we're just going to pick up recording here. Here's how we've gotten started. We have a couple different ways of doing our area over here that you will need to know. I just drew over my squared there. I don't want to do that. And we're going to generally do our volume is integrating up our areas. If you are doing this in terms of x, then your cross section has to be perpendicular to the x-axis. If you are going to do this in terms of y, your cross section has to be perpendicular to the y-axis. And that's going to be kind of our key to knowing whether we integrate this in terms of x or in terms of y. Now, before we do any problems, I want you to just see what this would look like. It's hard to find a good visualizer thing online. So this region that I'm going to show you isn't the exact one that we have, but it's enough to show you like what's going on. Okay? So I've got this little visualizer thing, and this is kind of similar to the equations we have. It's not. They're different equations, but I can't change them, so we're just going to roll with it. So what the visualizer does for us is it lays that flat, kind of like I was saying, like the graph is flat on here, and then think about the cross sections. They're going to come up above that. So if we did square cross sections, let me see if I can get this to work in here. Okay. Oh, I need that. Okay. Well, maybe it's not. Why is this not touching? Oh, I thought this was going to work so I could record it. Hold. So here we go. If you have a square cross section, there's the graph, and it's literally like they take that square cross section and sit it up 3D off the graph, like a little sheet of paper. And so the more of those that we add, if I can do this slowly, if I add in, let's say we want square cross sections the whole way out. I'm going to go the whole way out here so you can see as I add them in, the more cross sections you have, it's kind of like the Riemann sums, like you were saying. The more and more you have, it makes this whole volume shape 3D above it. So if it's square, what we're doing is we're taking the areas of each of those squares and adding up a bunch of them. So the integration is saying we're adding it up from here all the way out here.
So you'll
okay?
stick with the same shape.
The very similar shapes, but you could say, and we'll do an example here in a second, like here's a region. Let's do it with squares. Now let's switch the base to this. Now let's switch the base to this. So like to picture the other ones, an equilateral triangle. Let me go back to this. So if you had equilateral triangles, if you had a few of them, it would look like those standing up. And then the more you add in, it makes an entire shape. But you see how the volume of the shape would be different because that has like the point that would come almost like a mohawk looking thing going down the middle. And I can rotate that a little bit for you to see all the sides of it. Okay? If you did semicircles, let's do semicircles. Semicircles, you'd have those kind of standing up that way. And then again, the more you add in, the more it creates that full volume that you're finding. And you can kind of see that one, the best view was that way. It's curved over the whole top of it. Does that kind of give you an idea of what we're looking at?
Yeah.
Okay. Knowing and being able to see that is a huge deal.
So how do you know when to use what though?
They will tell you. Now it's spinning. Look at that. All right, so we're sticking with the region we have above. This one, we've got the base is the shaded region above, and they tell us what kind of cross sections? Square. So for square cross sections, what did we say the formula is for the area of a square? B squared. We have already expressed what is B. The B is the base, but right up here, look. We set up at the very beginning what is B, and we're going to do that on every question. That is the side of the square. That's going to be like the point of how we set that up. So when I set up my volume formula, I'm going to set it up as the integral from, okay, and also notice this also tells us that we are perpendicular to the x-axis. Because we're perpendicular to the x-axis, we're going to go all in terms of what? X. All right, so I need to integrate on this region from my lower x boundary to my higher x boundary. What's my lower x boundary? 0.2387 up to my higher x boundary, which was what? 1. And in place of a of x, we're putting in what is the area of a square? Well, the area of the square is the base squared, right? Yeah. And what did we say is the base? Root x minus e to the negative 3x dx. That is all the setup you have to do. This kind of question with those boundaries and that kind of integration, calculator, right away, okay? Do you feel like we need to practice typing those into the calculator? No. I do not feel like that is a challenge to us, yes? All right, so then let's try that again with a different shaded region, or the same shaded region, excuse me, shaded region above, this time semicircle. Yeah.
Why didn't we do like the 1/2 pi and 3/2?
Well, because in this one, this is now not a circular region at all if we use those square cross sections, because like we said in the visualization thing, the squares stand up and it makes the entire area. All you're doing there is saying, now this is not a square and I get that, but it's like you're taking a square and setting it up on this, but making like a million of them and adding them up. So there's nothing about that is circular. So that's why that pi in front of the other volume formula has been lost. When we rotate something, no matter what shape it is, it makes it circular. Like if I take a square and I rotate it, it makes it a cylinder, right? So everything's circular when we're doing rotations. Where this, when we're setting up the cross sections, we've lost the rotation part of it, and therefore some things will not have pies. They will only have pies if it's like this one, semicircle base. So if we're going to do a semicircle base, some of our volume formula is not going to change. Our volume formula is still going to start with the integral from 0.2381 up to 1. This time, though, the area formula is now dependent upon that base and dependent upon the semicircle thing, right? So going back up to my formulas, we said this is going to be our formula for a semicircle base. So I am going to do 1/2 pi, and it's b over 2. Well, what's our b? Root x minus e to the negative 3x all over 2 squared dx. Okay? And as long as you can type this in properly to your calculator, you're not going to have a problem. That one, if you're going to type it that way, I'd make sure I'd use those fraction boxes on my calculator instead of, I wouldn't be using all the parentheses everywhere. You're going to get yourself messed up. So do the little fraction boxes to type that in and then square it. That would be the key. Okay? All right. One more on this one before we do another region. If we do the volume of the solid, the base is the shaded regions above, cross sections taken perpendicular to the x-axis. Okay, so here's the rectangle one. I couldn't give you like a specific rectangle formula above because we don't always know what height they're going to give us. This one says the height is 5 times the length of the base. So in other words, they're saying height is 5b, yes? So normally a rectangle is length times width, right? Or height times the base. This is the height. What is the base?
It's given to us.
The base is the b still. The base is still this length b. The height is 5 times that as I go up. Right. So what's a good area of the rectangle formula for me to use here? 5b squared. Okay, and in place of the b, we'd put in root x minus e to the negative 3x all squared dx. Same boundaries.
Like b squared kind of thing, but we did times 5.
Yeah, so normally we do length times width, but we said the base is like the length side to side. The height is 5 times the base, and if I multiply that together, I get 5b squared. Does that help?
Yes.
All right, so we're just going to set up a couple other ones on the next page. Then we shall be done. All right, so this time we have, this is like from the ground up. Haven't done this problem yet. We're going with a different setup, all the other things. This time we're going with the y-axis probably. So we've got g of x equals e to the x side note, how important in this unit are your parent functions?
Very important.
Like shockingly important, right? So if we didn't know how to graph those before, we do now. Or we better by the test. So there is that. There is e to the x. So our region is bounded by e to the x, the horizontal line y equals 3. So I know, because I know my parent functions, that y equals 3 is above that, right? And the y-axis. So here's my region. Okay. There's my sketch the graph. Now, because I know what's coming, I really kind of want to know what some of these points are for myself, okay? This point right here, we know what this point is. That's 0, 1, because I know where that intersects, right? Yeah. What about this one over here? I know one part of it. Do I know the x or do I know the y? We know the y is 3. What's the x? You're saying e to the x equals 3. Therefore, x is the ln of 3. Okay, we all okay with that? Again, parent function, solving, all of that. Yay. All right, so this time, take a look at all 3 questions that follow. There's a bold underlined word in every single one. And all of these, my cross-section is now perpendicular to the what? Y-axis. So this means before I ever get started, I need to show for myself, kind of like on the volume ones that we've been doing, we do big R, little r. This time we're just going to draw, this is B, the base. Why do I draw it that way instead of the other way? Because it's perpendicular to the y-axis. Okay? I got to go side to side if it's perpendicular to the y-axis, up and down if it's perpendicular to the x-axis. Yes? Okay. If that is B, I need to be able to express the distance of B. And then what did we say when it's everything's with the y-axis? What are we going to be doing this in terms of? Everything's going to be y values. So what does that mean I need to do in order to find what B is? Take this equation and solve it for what? For x. So if this is y equals e to the x, and I want to solve it and put it in terms of y, ln of y is equal to x. That is my B.
Everything's like all combined.
Oh, I know. It's amazing, isn't it? So your B for all of these problems is going to be the ln of y. Okay. Why do I not have to do any subtraction? Because it's to 0. Technically, it's this side minus this side, but that side's 0, so it doesn't matter. Okay? All right. So let's set up the first one. Question 2. All right, we got what kind of cross sections in question 2? Square. So what's my area of a square? B squared. So let's set it up. Volume equals. I'm integrating now on what kind of boundaries? The y's. So look at our picture. 1 to 3.
Do we need to put the pi out in front of that?
So this volume formula has no pi because we're not rotating anymore. No circular. This one has none of that. So if I'm going to do the area is b squared, what is b? ln y.
Grant for share needs to leave for tennis.
Area of a rectangle formula for this one. A is, what's the bottom? B times what's the height? 5. So it's not 5b squared because we're not saying it's 5 times the base. It is just 5 set. So we'll do the same volume formula. Integral from 1 to 3. What is my b for this picture? ln y dy. All right, now this last one is a shape we haven't seen yet. Okay? This one says isosceles right triangles. How do you find the area of a triangle? 1/2 base times height, but what does isosceles mean? The legs are the same. So in case of this one, it means it's going to be 1/2 b squared. Okay? So if I do that, my volume's still going to be 1 to 3, of 1/2, what is our base b? ln y squared.